Ryan Betts is the CTO of VoltDB, a database with in-memory performance and streaming analytics. Ryan, welcome to Software Engineering Daily.
Hi, thank you, Jeff. Thanks for having me.
What is VoltDB?
Well, VoltDB is an in-memory database that's been designed to enable applications that need a combination of streaming analytics with traditional transactional workloads. So essentially, VoltDB looks at the world and it sees all of these really fast data feeds out there coming from logs, from sensors, from devices. And we ask ourselves, what would you need to do to write a database that could support real-time, event-oriented, operational applications against those feeds of data? And that's the tool that we've built. So VoltDB is, in more technical terms, it's an ACID, SQL, relational, in-memory row store. It distributes work across a cluster. It has built-in fault tolerance and built-in geo disaster recovery and a lot of integration features that maybe we can talk about a little bit later. And people use it to write essentially modern OLTP or online transaction processing applications against very fast streams of data. Volt can process thousands to millions of events per second, and for each of those events, it can run a multi-statement stored procedure or ad hoc SQL statement combining the ability to use SQL and Java in a single transaction.
I saw an interesting talk with VoltDB employee John Hugg where he touched on the issue of whether or not your data set fits in memory. Why is this important?
Now, that's a good question. There's really a couple different types of data, and thinking about them discretely one from the other is a good way to approach this. So there is data that grows historically forever, right? John likes to call that forever data. I like that term. I also call it legacy data. That's the data that lands in Hadoop or in a warehouse, and it's essentially unbounded in size. And that's the data that you want to do data science against, that you want to explore, that you want to do historical analytics against. But when you want to write applications that use the effort that you put into your data science to write real-time applications that are running against real-time events, then you have data that really fits into a different dimension. And that's the data that largely fits in memory. In those applications, you're typically storing some amount of recent history. You're storing the tip of the stream of that unbounded data so that you can use that for real-time context. And you also are storing other information, maybe data about the devices that you're writing the application for, or customers, customer segmentation, device location, device version, and that other kind of dimension data. And that data is on the order of people or on the order of the number of devices. And those are all numbers that fit in memory in reasonably sized clusters these days.
Why is concurrency a big problem with in-memory systems?
Well, concurrency certainly doesn't have to be a big problem with in-memory systems. When Volt was designed by Dr. Stonebraker in 2008 or so, he and a team of researchers from Yale and MIT and Brown looked at a traditional row store, right? So kind of what we think of as a traditional database, like an Oracle database or a SQL Server or MySQL database or Postgres. And they did something very clever. They instrumented a server, a database, to count instructions. So they counted basically where a CPU spent its time as it ran a common OLTP benchmark called TPCC. And it turns out that there were a couple of major sources of overhead. One of them was concurrency, another was buffer management. And they said, well, if you want to make a transaction processing system that's remarkably faster than these traditional row stores, then you have to solve the problem of concurrency, meaning you have to be able to create the illusion that lots of concurrent users have their own view of the data, right, without allowing them to corrupt one another. So VoltDB solves that problem in a novel way. It divides data into shards, or we call them partitions, and then it allows each partition to be used in a single-threaded way by a transaction. And since each partition is fully in memory, and we don't block on users waiting for a commit or a rollback because of the way our transaction model works, it means that we can run transactions serially against the in-memory state. In practice, this means that we can saturate a CPU, not managing locks or not managing skip lists or not managing a buffer cache from data that's in memory, but instead we can just use that CPU to run the user's workload and do what they think is valuable, which is to execute the transactions they've defined.
Could you talk a little more about how VoltDB originated?
Yeah, sure. So Stonebraker had set out a while ago to sort of specialize systems to a purpose. And so this idea of specialization to a type of problem, in Volt's case to online transaction processing problems, is core to the origin story of Volt. So before Volt, Stonebraker had created Streambase, which was one of the original streaming systems, and then he had created Vertica, which was a columnar parallel distributed OLAP system for historical analytics. So that what was left then of the database market that hadn't been vastly improved upon by these architectures was transaction processing. And so the sights got set on that workload. And that's really where Volt started. It started from an investigation of why are traditional disk-based row stores so slow, an understanding of that problem, understanding the problems of concurrency management and buffer management, and then an architecture that solves those problems in a modern database that's scale out, that's in memory, that's very cloud friendly, that supports virtualization, that has built-in fault tolerance, and all of the things that we expect from a modern system, but that's often absent from a legacy database.
What is meant by the term NewSQL?
So I'm not a big fan of the NewSQL term, but it is a term that's out there. So I think to understand NewSQL, you have to kind of think about the historical or the recent context around NoSQL. So we had all of these legacy databases, and then we had some data management problems that were difficult to scale, as well as some cloud deployment problems that weren't particularly friendly to legacy database systems. And these NoSQL technologies emerged. As part of that emergence, there were a couple of vendors like VoltDB, and I believe you spoke to MemSQL, and they would probably fall into this category, who said, that's actually the wrong choice. Don't give up SQL, don't give up transactionality, don't give up all the benefits of a relational model all the time. You can certainly kind of have your cake and eat it too for many applications. And the people who took that point of view have sort of been called NewSQL. So in a way, it kind of just means modern relational database. And the thing that I don't like about the term is that it doesn't really imply why you would use the system or how the systems are different from one another. It's just sort of just a historical oddity, the term.
From a high level, VoltDB combines streaming analytics with transactions. How are those two things implemented together?
How are they implemented together? So VoltDB includes some features that you wouldn't normally find in a typical database that it uses to integrate with streaming platforms. So for example, in a VoltDB cluster, you can create a subscription to a set of partitions on a Kafka cluster, and Volt will, in an automated way, pull that data from that Kafka cluster, and it'll run transactions against each event, record each event into its in-memory database, process each one. We have a number of features that we use for streaming analytics. You can create capped collections or sort of coarse-moving windows in VoltDB. You can also create very sophisticated indexes, including indexes on functions. And we also support a very fast, fully transactionally consistent in-memory materialized view function, which is essentially a set of streaming aggregations that you can create declaratively with DDL instead of hand coding in another system. So using those features, which are all kind of streaming-like features, we can support the ingest of hundreds of thousands, millions of events per second, and we can update state in the database for each of those. In addition to that, Volt supplies traditional SQL interfaces. So of course, you can write an application that uses our drivers or our SDKs in pretty much any language that you want. And that application can make request-response style calls to the database to run a traditional transactional approach. And what we find people doing with Volt is combining these two things. So essentially, as analytics become more and more real time, there's this growing opportunity to support operational applications that use those real-time analytics to personalize results, to detect fraud, to validate compliance, to implement real-time pricing, real-time billing, to manage devices, to make sure that you're utilizing expensive resources in the optimal way based upon real-time analytics. And it really, to support those applications, you have to support both the ability to stream data into the system, to aggregate and analyze that data in real time. You also need to support that operational transactional application. And so Volt supports those both by having some features specific to streaming systems and by having a set of more traditional database interfaces that you can call.
So we'll get into some of that in more detail later on in the conversation, like materialized views. But first, what is Hstore?
What is Hstore? So when Volt was first started, the paper that backed the system was called Hstore, and that really stands for horizontal store, which is kind of a strange pun. The paper that came before it, that was the foundation of the work that became the Vertica database, was called CStore for column store. And so there's kind of a little database joke in calling the next one Hstore for row store, for horizontal rows. Hstore is still an active academic project. It's not a commercial system. It's not fault tolerant, for example. It doesn't really support errors. But it's used to investigate advances in memory row stores, and it's still used by a number of universities, I believe, as part of their research.
Could you describe the single-threaded execution engine of Hstore?
Oh, sure. Well, I want to make a distinction here, which I don't think is just pedantic, but let me describe how it works in VoltDB. So Volt and Hstore are not equivalent. They've diverged, and there's some differences that are important between them.
Right. I guess I should interject with VoltDB as an implementation of Hstore. Is that correct?
Yeah. So, I think I understand your question better now. So Hstore is two things, and I think this is kind of the confusion. Hstore was an academic paper that was written, and it provides a lot of the foundation for VoltDB, although there are some important differences in VoltDB that we found necessary as we productized the system. Hstore is also an academic database that exists. I think you could probably find it on GitHub. It's a project that academics use to test some of their ideas around database research. So Hstore, the paper, is a great read. It's certainly easy to find. Just Google Stonebraker Hstore, you'll find it. It describes the problem with traditional databases, why they're slow, and then proposes a set of changes that you could make, or an architecture that produces a system that's not slow. So some of the key points to that are what you mentioned, that VoltDB uses a lot of single-threaded processing to process transactions. So I like to approach the explanation of this verbally through a kind of a build-up analogy. And I've written a longer piece on this that's more technical that perhaps we could link from your website that gives a lengthier description of how VoltDB runs transactions and why it's ACID compliant and fast.
Yeah, I'll put it in the show notes.
All right, that'll be good. It's easier to explain, I think, in writing. But you can take a simple thought experiment that if you had one CPU and some memory, and you wanted to be able to run as many transactions against that CPU as possible, and that was your only concern, what would you do? Well, one thing you could do would be to queue all of the commands to start those transactions in a queue, and then just let the CPU take a transaction off the queue, run it, and queue the result. Right, take the next one off the queue, run it, and then queue the result. And if you picture that, it's easy to imagine that you could fully saturate that CPU running transactions. Right, that CPU would be 100% busy, and all of the work that it was doing would be the work that the user wanted done. Right, the logic and the application that the user had coded. That's essentially how VoltDB works, except that we take that and we scale that across a number of partitions within a server, and then we can scale a cluster by adding many servers to a cluster. And we have a synchronous logical replication scheme that creates fault-tolerant copies of partitions that are fully ACID compliant. So
yeah. Sorry.
But that abstraction is sort of the fundamental abstraction behind VoltDB.
Yeah, John Hugg described it as concurrency via scheduling rather than shared memory.
Yeah, exactly. So as transactions arrive in Volt, we route them to the partition that they need to execute, and we put them in order, or we schedule them, right, for a linearizability isolation model. And and so we're essentially ordering the work to be done and then doing the work in that order. I like that term. I like that phrasing, that you concurrency via scheduling and not via shared state. So it summarizes pretty succinctly how it works.
Yeah. So Michael Stonebraker is the author of the popular paper One Size Fits All. One Size Fits All, an idea whose time has come and gone. And as you mentioned, he's heavily involved in VoltDB. Could you talk more about the trends that Stonebraker talks about that are exemplified in the implementation of VoltDB?
I think a lot of these trends now, we don't really take them as trends anymore. We just take them as facts. There's a lot of things that were very true in that paper. The first is that essentially big data exceeds the capacity of a single system to process it. You could almost take that as the definition of big data. If you want to solve big data problems, then you need to begin to specialize the tools that you use to solve those problems. And if you look at big data, there are a number of different aspects to it. There's a volume aspect, right? Vast collections of data that you want to be able to parse and analyze. And there's a velocity aspect, high frequency incoming event feeds that you'd like to be able to support real-time applications against. And so the one-size-fits-all paper says that you can't have one universal database architecture that's best at both of these problems. Data is really physical, and the way that you store data, the way that you organize it in memory or on disk, and the way that you schedule work against it has a drastic impact on the kinds of problems the system is good at solving and the kinds of problems the system will not be appropriate for. And that's really the fundamental idea of one size doesn't fit all. So if you have a large, hard problem, a large and difficult problem to solve, then you should break that into smaller pieces, and you should use specialized systems that will be best at each piece. So you should have a system specialized to volume, a system specialized to velocity, for example.
And could you contrast OLTP and OLAP as you see them in modern systems?
So OLAP is really a reporting function. OLAP is essentially store and report, right? It means collect data that you could be collecting that data in real time, but then query it in bulk. So typical queries in an OLAP system will scan lots and lots of rows of a system. They are asking questions often about the entire data set. You use OLAP queries to create reports of a period of time. You might use an OLAP system to scale some kind of data science or research activity as you're investigating a data set and asking questions of it in bulk. So OLAP stands for Online Analytics Processing, and that's sort of the problems that it encompasses. OLTP is really what people might think of as more traditional operational databases. So OLTP stands for Online Transaction Processing, and it puts transactions first. So in an OLTP system, you're creating and updating, replacing, and comparing usually a small number of records at a time, but often in modern applications at very high frequency. So if you have a record-oriented or row-oriented problem, it likely fits into an online transaction processing system or an OLTP system. If you have a problem that's about querying a very large data set and having a query that touches most of that data set, then you probably have an OLAP or online analytics processing problem.
There may be some listeners who feel a little bit out of touch with this conversation, so to help bring them in, could you contrast row stores and column stores?
Oh, yeah, that's a good point. I'm kind of making some assumptions, I think, here that maybe aren't good to make. So, I had said that data is really physical, and the way that you organize it matters. And so there's a lot of different ways to organize data. In the relational world, there are two common approaches, row stores and column stores. A row store is really easy to picture. So in a row store, you're storing one record after another in a line. So if I have a record that is, for example, my name and my state of birth, then on disk it would store, Ryan Betts, comma Ohio, and then it would have the next name and that person's place of birth. And after that, the next name and that person's place of birth. So the records are sequential one after the other in their storage medium, whether that's in memory or on disk. And that's a row store. So a column store is different. So what a column store does is it stores all of the entries for a given column contiguously on disk. So in that example, it would have Ryan Betts, my name, and then it would have the name of the next person in line and the next person in line. All of those values from a single column would be contiguous on disk. And after that, you would have a column that had all of the people's places of birth on disk or in memory. And that's a column store. So a column store stores disks in column order, essentially, and a column store stores data in column order, and a row store stores the data kind of record at a time. And so why does this matter? So if you're changing a person's record, or if you want to know information about a device, then typically you want to know most or all of the attributes of that device. And so you want to be able to fetch and retrieve them with locality. You want that data to be close together. And so a row store is favored. But if you're asking questions of a large data set, often you only want to know, you only need to access some portion of a record. So let's say that I wanted to understand, birth trends over time, and I wanted to kind of measure that by state. And I had 50 or 60 or a couple hundred columns in each of my records in this database, but I only really wanted to scan a couple of them. Then I don't want to have to skip over all of the data in the record that's not of interest to me. I just want to be able to find the columns I want and read them in their entirety. And so in that case, the column store is favored. Does that help explain it?
Absolutely. To circle back to the conversation about OLTP and OLAP, is there an overlap between OLTP and the notion of streaming?
One of the trends that we're seeing is that analytics are becoming more and more real time. And I think there's a number of logical trends behind this. One is that no one really likes to manufacture stuff in batches, right? So anyone that's studied manufacturing or sort of operations control knows that just-in-time processes are favored. And so streaming analytics is sort of a form of just-in-time processing. I like to call that continuous reporting to contrast it with OLAP systems that are essentially batch reporting systems. But once you have these real-time analytics, you want to be able to use that information in applications. So whenever you're producing analytics, you have to ask yourself why, right? This is true if you're measuring yourself, you're measuring your employees, right? Why are we measuring this? And what am I going to do with the information, or what am I going to do with the wisdom that I gleaned from having measured something? And what we're seeing is that as you begin to do analytics in real time, there are many applications where you can benefit by integrating those analytics into your operations. And that sort of intuitively pulls together the streaming analytics function with the transactional application. You want to be able to support both in a single system. Right? You want to be able to have access to both. There are also a lot of cases and a lot of workloads in streaming systems that require some amount of state. And people who've used, for example, systems like Storm or even Spark will have seen this. They'll end up running little databases beside those systems, either to store analytic results so that they can be queried or used by applications, or to store dimension data, or to store intermediate results. Right? All of that state management works really well and without any fuss in a transactional operational database. And so there's some benefits for many use cases in combining the two.
Could you define the term complex event processing?
Yeah, complex event processing is kind of an older term that's sometimes used for streaming, and the idea is that you're looking for patterns. And so there were a number of complex event processing systems that were made that are kind of a different technology from what we think of today as kind of the modern streaming systems like Dataflow or Millwheel or Storm or Spark. So CEP was really about looking at a series of events, running a lot of rules against it, and trying to find an outlier. Right? It's kind of like looking orange, 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 orange. I see an apple, and I kind of want to do something. And that's kind of what CEP systems look like.
Sure. So in that that John Hugg talk that I saw, he discussed the predominance of the ZKSC stack, which is Zookeeper-Kafka-Storm and Cassandra. Could you talk about some of the themes within the ZKSC stack?
Yeah, I think that when John talks about that really more as a warning, or maybe even as strongly as a criticism.
Yeah, so, he discusses it in terms of there's hazards, and particularly points out the hazards of Storm in the stack.
Mm-hmm.
I think.
Yeah, so John has another term for this that I really like. By the way, John is one of the other founding engineers at VoltDB. John and I were two of the first engineers here at Volt, and have a ton of respect for John, and that's a great talk. So it would be great to get that link as well if other people might like to see it.
Yes, it'll be in the show notes.
So a lot of people are looking at problems and looking at the Apache menu and figuring out how they can glue a la carte Apache projects together to solve the problem. And I think sometimes they do that without stopping to ask themselves, what is it that they really need? And so we see a lot of people who say, well, I want to do some real-time counting, and I want to do some real-time aggregation, and I need to join a couple of streams of information together, and then I want to make those real-time analytics queryable, and then I also want to persist that data into a data lake or into a warehouse so that I can capture it for historical analysis. And so what are the tools that I need to do that? And I say, well, okay, I guess I need some kind of a tool for ingest. Oh, Storm looks like an ingest tool. And so they deploy Storm. Then, of course, they need to deploy Zookeeper with that. And I go, well, I can't actually query Storm effectively. And I have this metadata or dimension data about my incoming events. I need a place to put that lookup data. So you know what? I'll run Cassandra beside my Storm pipeline so that I can interact with some state as I'm doing this stateless processing in Storm. And I need somewhere to actually put the results of these analytics so that I can scale queries to them. I have thousands of users or a pile of applications that need high-speed access to the outcome of this pipeline. So where do I put that? Well, I'll put that in Redis or something like that. And before you know it, you've assembled this massive set of clusters with really complex interdependencies and failure patterns between them. It becomes really difficult to reason about what happens when an event fails, what happens when at least at once processing causes redundant events to arrive. How do you handle out-of-order events? How do you rescind data that maybe you've published? There's just a lot of work in that. But we think that we can make that much, much simpler, essentially by combining the streaming analytics portions with the transaction processing portions. Because then in a single system, you have the ability to do the streaming aggregations that you need for those applications, and that's integrated into the same failure model as the dimension data. And that system is also queryable directly so that you can read and even query and mix and match the analytics that have been produced all into a single platform. And so that's really our warning a little bit, I guess, about the Apache stack. We love Apache software. We use a lot of it internally. It's not by any means a criticism of Apache, but I think what it really is that a lot of developers haven't solved problems like this before, and it's natural that it takes a while to try to understand what patterns are good and what patterns are bad. And I would caution about patterns that require a large number of interoperating systems.
And this dovetails nicely into the discussion of using VoltDB as a substitute, or I guess maybe an augmentation to the Zookeeper-Kafka-Storm-Cassandra stack. How do people, or do you typically see people that already have the ZKSC stack? Do they gradually migrate, or do they drop out that entire stack and plug in VoltDB, or do they augment their stack with VoltDB? How do you see this transformative process?
Yeah, so what we see is that when someone wants to be able to support an application that actually uses the analytics that they're producing, then they're forced to rethink their stack, and that can become a transition point. The other thing we see is that these high-speed or high-velocity applications are still very new, and so they can have relatively short lifespans. So a lot of times these applications are sort of reformulated in relatively short order. If you talk to, I'm sure you know this better than I do, Jeff, but if you talk to people who are running big SaaS infrastructures, right, they're continually changing and reordering some of the components that they use as their problem sort of evolves. And so those are sort of the different inflection points. The way that I like to think about this adoption cycle, I have a couple of different ways to think about this. But one is, I think that people go through a collect, explore, analyze, and act cycle as they solve big data problems. So the first challenge they have to solve is just how do I collect all of the log data or all of the event data into a single repository. If you think back to conferences several years ago, it was all about event collection frameworks. We don't hear much about that anymore. It's sort of a solved problem. And once you've collected that data, right, then you need to start doing some data science against it. You start looking for statistical patterns or customer segmentations or trends that you could predict against. And some of those learnings are going to be about long-term trends. Some of those learnings are also going to be about things that you can do in real time operationally to improve customer experience, detect fraud, use resources more optimally. And in that case, now you need to write an application that does that, right? And so that's really that act phase. So once you start writing that application, then you're going to need some way to support an application with a database, and that typically means some kind of an OLTP system.
I imagine there's also a lot of froth in this is more of like a business type of point to make, but I imagine there's a lot of froth in the economy right now. So, if some CTO in a company that's about to go under is using ZKSC, and near the end of the lifetime of his current company, he says, gosh, if only we would have integrated all this stuff into VoltDB, we wouldn't have had this miasma of problems. And then when he goes to start his next company, maybe he can just use VoltDB from the ground up. Is that a valid scenario to imagine?
Yeah, I think people, are learning lessons and they're figuring out what worked and what didn't work. I like to look at that from a slightly more optimistic point of view. We very regularly see people take Volt with them from job to job. So once people understand the value of the combination of streaming analytics and transactions in a single platform to support real-time applications, and once they see the pattern and how Volt solves that, then it's very frequent that someone might leave a job and bring Volt with them to the next.
Could you talk more about the advantage of having this set of systems integrated into VoltDB versus having this multi-technology approach? Like, what are some specific pain points that you can avoid?
Sure. Well, one is that as you begin to assemble these things into really complex pipelines, there are two problems that are primary. The first is that you create a lot of excess latency and excess communication between all of these components. So you're exchanging data between them all. You're paying a latency cost, a network cost, a storage cost. You're reading and processing all of that data multiple times in separate systems. So the first is simply an efficiency and performance penalty that you're unnecessarily paying. The second is that they have really complex fault patterns. So I think the best description of some of the complexity of these fault patterns that I've seen is actually in the data flow paper that Google published. But what happens in these event-oriented systems is that events don't arrive in nice, ordered, neat ways. They arrive out of order. They arrive multiple times. Sometimes they don't arrive at all. And then upstream components fail. Different parts of your pipeline fail and need to be recovered. That causes more data to be seen twice or skipped. All of that you need to be aware of and you need to handle somehow. And so if you've coupled lots of systems together, then you need to ripple the corrections for those errors through all those systems. And it makes it very difficult to create anything that's close to correct or even understood in some cases. The people who build these application stacks, they realize this. So, for example, a key point of the Lambda architecture is that you shouldn't really rely on your real-time system being accurate, and you should just correct it with a batch process every now and then. Right? That's really an explicit acknowledgement of the fact that it's extremely difficult to manage accurate fault tolerance when you have all these systems coupled together and all processing the same data. So it's certainly important to use the right tool for the right job. We do absolutely advocate for people to build pipelines, but we think that each stage of that pipeline should have a distinct purpose and should be relatively self-contained. There are many, many Volt customers that use our Kafka integration to stream data from Kafka to Volt, use Volt to perform real-time aggregation, filtering, enrichment, and then use Volt to support the operational applications that need access to those analytic results. And Volt also has an integrated export function so that you can push data out of VoltDB using open source, user extensible export plugins to downstream systems like a Vertica system or Hadoop or an OLAP store, or even back to Kafka for another application.
You mentioned Lambda architecture. What is your definition of the Lambda architecture?
So I think Nathan Martz's definition is the common one, and it's essentially a system that uses some kind of a streaming platform to produce aggregations or analytics in real time that then get refreshed by a periodic batch process.
Great, that's useful. So we've talked about VoltDB and various trends in the database world, the big data processing world. I'd like to circle back to a naive question because this is Databases Week. What is a database?
I gave a presentation to a couple of our young BDRs about what is a database. And so I thought about this question for longer than I maybe ever would have imagined I would have on what the simplest way to explain what is a database. So my simplest explanation for a database is just a system that combines state management with computation. So a database is just something that holds data and allows you to compute against it. I think that's fundamentally what a database is. And then you can start to think of all of the different flavors and variety of data that you might like to store, and you can think of all of the different types of computations and queries and transactions that you might want to run. And from that, you can see the diversification of database architectures. But fundamentally, a database is just a container for data that enables computation against that data.
Interesting. The Wikipedia definition is a little more conservative.
I don't doubt it, but I take an expansive view of the world as a database.
Oh no, I mean I'm with you. Like I think the Wikipedia definition was a little dusty, and it was kind of a motivation for. I mean, as I'm talking to these different people, Rethink DB, for example, has push in the database. It's like, since when is a database something that can push data to you?
Yeah. Well, I think that's actually I love that feature in Rethink DB, and I really like the way that they've done that. Volt was originally incubated within Vertica just as part of the founding story of VoltDB. And so one of the first things that we did was think, well, how do we integrate Volt and Vertica together? Right? How do we use Volt for transactions and Vertica for analytics? So one of the first things we wrote was an export function. And so export or push from Volt has been a feature since the first public release. And I think when you start to think about how do systems interact with each other and how do they interoperate, you have to stop thinking of a database as the terminus for a process, right? I think a lot of people naturally think about data goes to a database and just stays there forever. But that's just not the case anymore. Data is now flowing through databases, is flowing from one to the next and coming back in the form of analytics and reports, right? They're much more dynamic. And so I think a broader definition is necessary, especially as you look at the proliferation and the really richness of systems that have been created over the last 6 or 7 years.
And that push-based export functionality that Volt has enables something that John Hugg described as data lifecycle ecosystem. Could you describe how you are seeing users build out that data lifecycle ecosystem? And maybe you could describe that term.
Yeah, so there are a lot of cases where you receive data and that data needs to be manipulated somehow before it can be frozen and stored forever into your OLAP system or into your data lake or into Hadoop or whatever it is that you're using. And so the data goes through a life cycle, right? I actually like to think of data when it's born as being kind of primordial, right? Oftentimes you want to create a session out of data. You have multiple, business processes or multiple APIs or services, and you want to combine the records from those services into a single session and persist that record. You see that a lot sort of in call detail record in the telecom space and places where there's big APIs. You want to record multiple events together. And so and a lot of times you want to be able to enrich data. You want to be able to add dimension data to it. Oftentimes you need to manage some amount of state even to interpret data. So in a lot of sensor networks, sensors don't provide particularly rich or clean inputs to the back-end system. So think about a sensor that's just telling you its current velocity, its current speed, right? I'm currently going 60 miles an hour. I'm currently going 55 miles an hour. Well, the questions you want to ask are, well, are you slowing down? Are you speeding? How long have you been speeding for? All of that requires that you can remember a little bit of recent state about that sensor. It's not going to repeat that to you every time. It's just going to tell you the current reading. So you need to manage the state to construct what it's actually doing over time. So data goes through this sort of cycle where it's changed really rapidly. It's kind of completed, put together, sessionized, enriched, filtered, and then it gets frozen and stored into an OLAP system. And once it's in that OLAP system, there's usually some kind of an historical reporting that runs. I like kind of customer or market segmentation. I have 100 different descriptions from my customers that describe the 100 common behaviors they might have, and I want to assign my segmentation behavior to my customer base. And I want to bring that report, right, the results of those analytics back to my real-time system so that I can write real-time applications that treat customers based upon their preferred behavior, based upon the data science I've done. And so there you have sort of a total life flow of data. New data is arriving, it's kind of being born, assembled, filtered, enriched. Once it's complete, it's placed into a large repository to be stored for historical purposes. Once it's in that historical repository, you're going to report against it, do data science against it, and you want to take the results of those analytics and use them in real-time applications.
We go back in time. High-frequency trading firms were an early customer for VoltDB. What was the common use case that high-frequency trading firms needed out of VoltDB?
So I can't speak to those use cases for NDA reasons, but I can talk about some of the common use cases that financial companies use VoltDB for at present. So
Sure.
people use VoltDB for a lot of post-trade compliance analytics. So as you're trading and as orders are coming and going across the market, there are a lot of different things that you need to know about them for compliance reasons. And so people use VoltDB as a message database to store post-trade information to support the many applications that require that data downstream. Some of those are real-time compliance. Some of them are required for auditability and kind of features like that. Another kind of common problem in financial institutions is managing real-time position. So you have a lot of different ways that you're trading, a lot of different trading desks, maybe some trading algorithms, and all of these things are changing a firm's exposure to the marketplace really rapidly. Right? So one algorithm might be buying a lot of Microsoft, and another algorithm might also be buying a lot of Microsoft. And you want to understand, what is my firm's total exposure to something bad happening to Microsoft in the next several seconds? That basically requires a really fast kind of giant scoreboard that can maintain the position that you have on all of these symbols, and that's another common case for a high-speed system like Volt.
I think the high-frequency trading use case was one impetus for materialized views. You touched on materialized views earlier. Could you define a materialized view?
Yeah, a materialized view is a table that is summarizing another table. So, I think you can think of a materialized view as just a declarative grouping or aggregation. And what VoltDB does is it allows you to define a materialized view, which might say, group data by this attribute, sum it by this attribute, average it by this attribute, and then keep those statistics or those analytics available in memory so that they're really fast to query, and keep them updated as data changes. And so people define materialized views in Volt to define the streaming aggregations that they require, and then they can use them in real time. They can use them in transactions. They can query them from the system with ad hoc SQL. They can access them any number of different ways. So, kind of I think a while ago, John and I wrote a blog post together that was sort of a joke, but also really quite serious. It was, I'm trying to remember the exact title. It's something like VoltDB introduces incremental map reduce. So you can kind of think of materialized views in that fashion as well. That the views are essentially streaming distributed reducers that you can then query on top of to recombine.
Does VoltDB offer probabilistic data structure support within its materialized view functionality?
It does, yes. I had to stop. Some of these features are just emerging, and so there's a couple of different ways that VoltDB supports probabilistic work now. One is that you can integrate things like hyperloglog directly into Volt. So the fact that Volt can run third-party code through its Java stored procedure model is a really powerful extension point for things like this. So you can store hyperloglog records in Volt, and you get full interactivity through them through your transactional stored procedure model. You can put them in views, you can do whatever you want with them and access them. And you can write views on functions of columns. So anywhere there's a column function in Volt, you can write a view on that function. VoltDB also recently added support for approximate count problems that uses hyperloglog as an internal representation. So you can get very efficient approximate counts across the cluster. And you can do that directly through SQL and Volt.
Maybe this is getting too subtle for a database discussion, but could you outline some of the common probabilistic data structures? Because they seem to crop up within this discussion of databases. I know there's Bloom filters and hyperlog logs, and I think there's some other ones, but maybe you could touch on them.
Yeah, that's a good question. The ones you've listed, I think, are certainly the most common. I think what maybe is more useful is just to identify kind of what they are. So a probabilistic data structure trades accuracy for space almost always. So it says, I'm going to give up perfect accuracy, but I'm going to bound my error by some probabilistic limit. And because I'm willing to make that trade-off, I can then store the data in a much, much smaller space. So you're essentially trading probabilistically bounded accuracy for space. And they've become relatively popular algorithms. We see where we run into them almost exclusively in Bloom filters and in hyperlog-log implementations are kind of what we're seeing. People use hyperlog-log, if people aren't familiar with that term, to do a cardinality estimation. So roughly how many items have I seen from a certain set, essentially.
Could you talk more about how VoltDB handles sharding?
Yeah, VoltDB assigns the rows in a table to a partition using a typical consistent hashing scheme. So I like to describe this just with relation to a key value store. People tend to understand pretty intuitively how a key value store might map data across a lot of shards. Essentially, it assigns each key to a shard. VoltDB does the same thing, except that it assigns rows to shards. So when the user in VoltDB defines a schema, they indicate which column of a table should be the partitioning column, or kind of in NoSQL terms, which column represents the key for that row. And then we run that through a consistent hashing algorithm to identify which partition will store that particular row.
You are the CTO of VoltDB, which is something of a management position as well as a technical position. I'm curious about the management aspects of running a database company, particularly ones that are unique versus other engineering management type of positions. Do you have anything interesting that comes to mind when you think of things within managing a database company that may be disjoint from managing other types of companies?
Well, I think that managing companies, there are common principles across them. Right? Financial discipline, managerial discipline, operational discipline. But there is one thing that I think about a lot about Volt, and that's the fact that when people buy a database, they're really entrusting you with something that's incredibly valuable, right? So in VoltDB's case, many of the applications that people deploy on VoltDB are directly revenue generating. And people are trusting you with their data, they're trusting you with their revenue, they're trusting you with their uptime and their customer experience. And managing and building a company that takes that trust to heart, makes that, earning that trust part of its DNA and all of the things that it does, and the way that it's open in its development, and the way that it's open with its internal communications, and the way that it manages customer support. I think for me, that's maybe one key thing about Volt. And of course, all companies want to be trusted. I feel that there's a special responsibility when you build a database, though.
Do those responsibilities limit the ability to scale the workforce aggressively? Because it seems like maybe if you have to maintain this high degree of reliability as a database, you can't have a bunch of engineering initiatives going willy-nilly. Maybe you have to do a little more serialization in terms of the types of things that you work on, or maybe that's totally off base.
Yeah, I don't think that's necessarily true. From the first day that we started Volt, we took testing and automated testing and continuous integration really seriously. The continuous integration kind of technology that we've assembled here within Volt is awesome. So every time the database is built or changed, we of course run a very large unit test suite. We run a large integration test suite. We run hundreds and hundreds and hundreds of performance tests every night. We have automated torture tests kinds of running against clusters. We have just a ton of continuous integration, and that really lets us iterate quickly. So our development teams at VoltDB, we work in small Scrum teams, usually 3 to 5 people in size. We run 2-week sprints, and we release every other sprint. So we release Volt roughly 12 times a year. And we expect each of those releases to be fully functional and completely reliable. So we take that approach. We certainly don't look at we don't really look at those two things being coupled: the inability to change the database with the requirement that you make it reliable. We take really seriously learning how to ship our database.
Well, Ryan Betts, thanks for coming on Software Engineering Daily. It's been a real pleasure talking to you.
Absolutely. Thank you so much.